This week we're focusing on something that's really important because it's almost guaranteed that you're going to do one of these, and you've done one of these already. So we're going to look at linear regression. Now, you really don't want to be doing these things by drawing something on a piece of graph paper and then taking a ruler and trying to fit a line through it. You actually want to use computer programs to do it. Now, last year you did a kinetics practical. If it went right, you'll have your own data. If it went wrong, they will have given you some example data. So this is the example data that we give out. So now, so this is what they would have given you. Let's ignore columns D to I. They gave you the tube numbers, the concentration of substrate, and the absorbance. Now, the way the experiment works, this was acid phosphatase enzyme catalysis. So what you do is you drop in something to stop the reaction from happening. So you work out the concentration of the product after you've dropped that liquid in to stop the reaction from happening. And then you have to do a little bit of a back calculation to calculate how much of the product was there before you swilled in this extra liquid. So then you can figure out how many moles of product you've got, and you can figure out, because you're always doing it over the same time, you can figure out how many moles were produced in a certain amount of time. So you can figure out the rate of reaction. Now, this is the great advantage of Excel. You can just put in the formula for that particular, doing that particular calculation. Then you can just copy it to all the other cells and you get it done with the same formula applied to all the other numbers. Just great. If you're doing repeat calculations of anything in a data table, I really suggest you use something like Excel to do all those calculations and not do it on a calculator one at a time, because it will remove the chances of you making any kind of mistakes. So that's all done. Now, if you were to plot the concentration of substrate against the rate, so as you plot column B against G, you'd get a curve, a Michaelis-Menten curve. Now, there are issues with fitting lines, well, fitting things to curves, curve to data, fitting curves to data. A line is described by two things. You only need two terms to describe a line. You need its slope and its intercept. So I'll call those A and B. Now, if I have something which has a single change in direction, so it's either a U shape or an N shaped curve, then that has to have a square in it. It has to have an x squared term, as well as an x term, which is part of your line, and a constant, just a regular number. So that means I now need three numbers to define it: ax squared plus bx plus c. So I've gone from two numbers for a line to three for a quadratic. If I have two changes of direction, then I end up with a cubic function. So it has to have x cubed in it. So I have ax cubed plus bx squared plus cx plus d being my constant, my regular number. You can see as I'm building up the number of terms of x and the complexity of my curve, I build up the number of things I need to fit my model. Now, in this case, there are 7 data points. Ignore the first one, and I'll come back to explain that. So ignore the one that's in tube 1 and the one that's in tube 9. They're just constants and really need to be taken out of consideration. Okay. So what you've got there is you've got 7 data points. Now I can fit a curve to it, which includes 8 or 9 or 10 different values of x to end up fitting a curve. But then my curve is more complicated than the set of data I originally had. So this is a process called overfitting. And the discipline that I came from, we used to do that all the time. So you'd figure out where the atoms were in a protein crystal structure, and you might have 10,000 atoms in the crystal structure, and you only had 4,000 data points from collecting your crystallographic data. So you were just creating data from nothing. It's always a bit dodgy when you do that. So overfitting is an issue. So lines are the best things that you can possibly do. They're nice and simple, only require you to figure out two things, slope and intercept. So what you do is you transform this S against rate, so concentration of substrate against rate graph, into one where you do 1 over the substrate concentration and 1 over the rate. So it's called a double reciprocal plot because these are both reciprocals, and it's also called the Lineweaver-Burke plot. Now, in reality, if you're going to work out Km and Vmax, you would not use this. You'd use an Eadie-Hafstee plot because the Lineweaver-Burke plot is very sensitive to errors. But we're going to use that just as a simple example because this is how you want to do a regression. So what you would do is pick your X and Y coordinates. You go to insert. We want to insert a scatter plot because that's what it is. So it's a scatter. And there's the scatter of your data. If you look at it, there's some things that make an obvious line. There's a horrible point over here. If I select that particular plot, I can add elements like adding a trend line. So this will fit a line through that plot. I want a linear one, not exponential or linear forecast or moving average. So it's nice. It gives you a preview about what it would do. So this is what I mean by overfitting. You can end up with all sorts of weird shapes and things, and a nice line, there it goes. So I put in a line. I can then fiddle around with the trend line options so I can get it to display the equation on the chart, and I can get it to display the R squared. Remember, the R squared is a coefficient of determination. So if I turn that into a percentage, that's telling me that the values of Y, 43% of their variation is explained by the variation in X. And the equation is Y equals 8.9856 times X plus 76.24. All looks good. I'm now going to delete that. So that's how I would do a linear regression in Excel. Now, the only problem, don't save, with that particular one is that outlier that I pointed out. So here are some nicer examples. So here's the example. This is the uninhibited case, and there's that nasty outlier. Here's the inhibited case. There's no outlier, and look at the R squared. It's 99.35%. Y equals 32.667x minus 165.59. So there's nothing wrong with doing it in Excel, except it really doesn't deal with outliers at all. So that's why I want you to do things in SPSS, because the key thing that SPSS brings to the analysis of linear regression is diagnostics and confidence intervals. And these are really, really important to know that you've got a good fit. It would be far too easy to run off and put that equation in and use it for predictions, even though it's got a poor R squared. It's not terrible. You'll see R squared's lower than that in many occasions, and it still be valid. But in this case, it's completely done because of that extreme outlier.